sure that we got like a code on.
Yeah. But you guys are sitting. I'm actually standing and walking a little bit too.
He's up there just jumping jacks. So guys, a stack.
Yeah. All right, let's get going. All right, so we are back to the stack topic. Last time we talked about the push instruction as well as the pop instruction. Okay, I also illustrated using GDB, what is happening to the stack pointer ESP, and also what is happening in the memory, where the stack belongs. Okay, we looked at where ESP points to, and also what ESP or what is about. What is the content of the addresses about where ESP points to. Okay, so we examined all of that stuff. So here comes a big question. I forgot to ask you guys to think about this one as a brain teaser before we left on Tuesday. Okay, so here's the question. Of all the instructions that we have talked about so far, is it possible that we can implement the effects of push and pop without using the instructions push and pop? Let's think about it. Okay, so what we'll do first is we'll go back and take a look at the programs that we wrote, or the program that we wrote on the other day. We'll go through GDB one more time, but for every instruction, we'll look at the effect, and then we ask ourselves, could we have done it using, instructions that we know already? Okay. So let's go back to the folder from Tuesday. So that will be 20313 cisp310, and the program is called push pop. Okay, so we'll go ahead and just rerun push pop. It's already compiled or assembled, so we can just go ahead and run it. We'll go ahead and look at line 6 first. Okay, line 6 is the first one, and then we'll run the program. Now we are ready to execute the push L instruction. The push L instruction does two things. It affects two different parts of the computer. First, it puts something into memory. It changes memory at certain locations. And second of all, it also changes the stack pointer in a certain way. So we'll go ahead and take a look at ESP at this point, and look at the value. Okay, and then we'll single step the instruction. The effect of the instruction we already know. We know that the stack pointer is decremented by 4. We also know the memory location of where the stack pointer is pointing at right now is what we pushed on the stack to begin with. 17 in hexadecimal is 23, so that means whatever the operand is with the push out instruction, that's the value. That's the thing that we push on the stack. So here's the question: could we have done this without using the push instruction?
Yes.
We could have. Yep.
Like move L or something?
Move L is one, but we need one more instruction. Move L is one, and the other one is
Indirect?
Hmm?
Indirect?
Indirect is the operand. But what else do we need in order to implement this? Add or subtract. Okay, either one works because you can add a negative value or you can subtract a positive value. So they should do exactly the same thing. Now what we'll do is we will copy this program, pushpop.s, to today's folder, so that we'll continue this discussion, but under today's folder. No one asked me to upload the actual files, but I guess the video is just as good because I go through the whole process in the video as well. So we'll go ahead and take a look at pushpop.s, and we'll just say that we want to implement this instruction. I comment it out, so that I can replace it with just 2 instructions at this point. What do you think would be the 2 instructions? We know we need either an add L instruction or subtract instruction. Either way is fine because we just have to control the constant that we are adding to it or the constant that we are subtracting from it. And then the next instruction is a move L instruction. The question is, what would be the proper order of these 2 instructions? What do you think? This turns out to be the right order. Okay, you want to adjust the stack pointer first. In other words, you're moving the bookmark to indicate the next 4 pages are now in use before you go and change those 4 pages. Okay, it's the same thing. Let's say this is the wild west. Okay, So, and this is back in the gold rush period, okay? And you stake out, you prospected, a piece of land, and you think, I think there might be some gold here. So the question is, would you, make your stakes first? Would you stake it out to mark that this is my spot, or would you start digging right away?
Dig.
Because while you're digging, somebody else would put the stakes around you, and then say, "Hey, guess what? You're digging in my hole." Remember, this is the Wild Wild West, so that sort of thing happens. So what you need to do is to stake it first to claim that it is yours before you do anything with it. It's the same thing with the stack. Somebody's gonna change the content if you don't claim it first. So the first thing you want to do is to, in this case, since I'm using the add instruction, I'll be adding -4 to the stack pointer, and then I'll just move 23 in and as an immediate operand to where ESP wants to. So these two instructions will replace the push instruction, and it does it does exactly the same thing, except now it is in 2 different instructions. Yep.
Add -4.
Sorry.
Adding -4.
Add -4.
Can we just
Subtract 4.
Yeah.
Same thing.
Uh-huh.
Yep. Okay. Any questions about the push instruction? No questions. No questions about the push instruction. Let's think about the pop instruction. Let's say that we want to replace this pop instruction with, instructions that we know already. Now we kind of know that this is kind of the reverse of a push instruction. In other words, instead of subtracting from the stack pointer, we want to add to the stack pointer to move it to a higher location, so that it points to a higher location, I should say. And we also want to do the reverse, and we want to copy from indirect ESP to the destination. In this case, the destination is the register EBX. So we kind of know the individual instructions already. We know there has to be an instruction like this into EBX. We also know that there has to be another instruction to add 4 to ESP. The question is, what would be the proper order to do this?
Right.
Yep.
First you copy, because if you're gonna move after you copy, then if you're gonna move after you add, then you're gonna be moving something else, not the correct thing. You're trying to copy, move first the 23 in there, right?
Okay, so
So
move first or add first?
The way you have it set up right now, so just give.
That is correct. Okay, this is the right way to do it, because you want to copy when you still own those 4 locations. In other words, as long as ESP is still pointing to that location, nobody should be modifying it. The background interrupts and stuff like that should not be modifying it. So this would be a good time to copy it first. Then you remove the 4 stakes, and then you say that, okay, if anyone wants to come here and dig some more, that it's fine. Okay, so this would be the proper order. What is kind of bad is, if you do it in the wrong order, if you flip the order, you kind of have to do an offset, but you can, kind of do it in the reverse way. But if you do it in a reverse way in this class, in this kind of environment, nothing bad is going to happen. It's only because interrupts are using a system stack instead of your stack when you are a user application. But it is not in general true. Not in general, if you flip the order of these 2 instructions or the 2 instructions earlier, your program can break, because if you don't claim the memory first, then somebody else can change it. Are there any questions at this point about using regular instructions to replace the push and the pop instruction? Yep.
Why would you want to?
Want to?
Want to replace them with move and add?
Because in a RISC environment, you don't have push and pop. You only have as basic as possible. So push and pop instructions can be emulated using individual instructions like move and add, and therefore with a RISC architecture, they don't have push and pop, simply because those instructions are not necessary. Yep.
So you said that we use a stack to put like last in, first out, but if we can use these kind of instruction, you said we can peek. How come we can't copy if we can say, okay, so this is our pointer and we want to move something, let's say, it's eight spaces behind with
You
this?
can change stuff that you own already. In other
Okay.
words, all the locations from where ESP points to and above, you can actually change those locations. But you have to be careful, because if you change the wrong location, very, very bad things can happen. Now, we haven't really quite, talked about, what kind of bad things can happen and why, because we haven't really gotten to the point where, those things can happen. But technically speaking, anything that is above, that has a higher address than what your stack pointer points to, you can change those. I mean, that's technically the stuff that, quote unquote, you own. Okay. All right. So we are pretty much done with the push and pop instruction. In the class notes, there's also two more instructions, or two more pairs of instructions. One is called push A, which means it'll push all registers, and the other one is pop A, which pops all registers. Okay, they're really handy when you're writing an operating system, because when you write an operating system, the kernel part of the operating system requires pushing all the registers to save the state of a process. And then it needs to pop all the registers or restore all the registers before another process can continue execution. So those instructions are designed mostly for kernel use, but from your perspective, we don't really have to use push A and pop A in this class. Yep.
So basically, push A is just like placing a stock of papers on a table and then taking it all again, like.
Push A is to push all the registers. It's basically push EAX, push EBX, push EDX, ECX, push EDX, push EBP, push blah 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 blah. So all your registers will be saved with one single instruction. But it can be done with without the push A instruction itself. Yep.
Is it still going to be last in, first out?
Yes. So the push A and the pop A is a pair of instructions. One will save all the registers, the other one will restore all the registers, and they work together to work correctly. Okay. Any other questions about push and pop instructions? Yep.
If you did push A, pop A, wouldn't you be popping just junk if you weren't using that register?
If you're not using that register, or you're saying you did not push that register earlier.
Wouldn't that be kind of inefficient unless you're using all of the registers?
That is correct, but that's correct. It is only useful if you are using all the registers, but that is the case when it comes to multiprocessing. In other words, every program that is in execution has quote unquote a state, and a part of the state of a process. Now this is way beyond the scope of assembly language programming, but the state of a particular process consists of many things. The state of the registers is one of the most important parts of the state of a process. So if you're writing a multi-threading or multi-processing kernel or operating system, you will have some parts of the program to save all the registers, and then another part to restore all the registers. So we are pretty much done with this part here. And going back to the notes, it's a good time to talk about call and return. Okay, so here's call and return, and this is also the old notes, because I did not feel any need to write it again. This is already sufficient. Okay, subroutines in C is pretty easy. Okay, so we'll start with a basic C subroutine, and then we'll convert it into the push and a pop. Call and return, and then we'll convert it to push and pop, and then we'll convert it to move and add L. So we'll go ahead and we'll write a silly .c program, because it is very simple. Okay, we have a void, f void, and inside here, let's say we have a global variable int x here. So f will just do the increment on x. And here's our main program. And it calls f, like that, and it returns. Okay. Obviously, this program doesn't do much. It doesn't do anything that is meaningful. In fact, it is really bad because it uses what? A global variable. Okay? Global variables are evil. They are evil. they're much worse than Darth Vader and many other characters. You have to understand Darth Vader, has reasons to be so, angry all the time. He's a middle manager. Well, first of all, he's a middle manager. Okay, he's in middle management, has a demanding boss, incompetent underlings, right? Okay, has a son who would not listen to him. So, and he needs a CPAP to sleep. I mean, that's why you hear that heavy breathing sound. That's actually his CPAP working, right? So, I really cannot blame the guy. I mean, I would call him more of a victim than an evil person.
Yeah. Take the anger out on another planet, right? Take the anger out on another planet.
That's your boss telling you to do it. Okay, so what we want to do now is to implement silly.c in assembly. So I'm going to copy this to silly.s, and then we'll take a look at this program and say, how do we implement this program? First of all, replace the beginning of every single line with a pound sign, so we comment out everything. And because x is a global variable, it has to go into the .data section because we are going to change it. So here we have .end. It's basically replaced by x.end. And in assembly you have to initialize it. So I guess in C I should do the same thing so that it means the same thing. Now it is time to implement the subroutine called f. Well, that's not too hard. The name of the subroutine is nothing more than a label, because the label indicates, oh, I forgot one thing, because when we switch back to the code part of the program, we have to switch back to .text. So we have to do something like this. F colon means that we have a label for the entry point of the subroutine. Okay, just like F open paren close paren with a void inside is the entry point for a C subroutine. So are there any questions about this part? Using a label to define the entry point of a subroutine. Not too hard. And then we want to increment the variable x, so we'll just say add L $1 to global variable x. This is a direct operand. And the next question is, oh, but how do we return?
Put another label down below. Put another label down by your call.
At the call?
Yeah.
Okay, well, in that case, I'll call f again, so that the goto won't work. Because the return point changes. The first call to f will have to return to the entry point of the second one, and then the second time it will have to return to the next point. So using a goto at the end of a subroutine is not going to work. Okay, so we'll try to figure out what to do with it. Now, on the other hand, how do we implement main? We don't really have main when we write a pure assembly program. We have the entry point called start, and then we have to use .global_start so that the linker knows what is the entry point of the entire program. That's pretty easy. It's just a name change, because we don't have a main function anymore. How do we call a subroutine in this case? Jump seems like jump should work, right? Because jump does transfer over to the entry point of f. But then how do we get back? You cannot just say jump back to this point here. Let's call this L1. Because this approach will only work when you have one and only one invocation of the subroutine f. If you have multiple invocations of the subroutine f, then jump L1 is not going to get back to the right place. Are we getting this part? Okay? All right. How many of you took cisp310 from me? Okay. How many of you still remember the return line number thing? There's no penalty if you don't. Okay, so what we need is a very similar mechanism. In other words, every time we call or invoke a subroutine, we need to set up something to remember where we are supposed to go back to. Okay, and then we get to the subroutine, we do whatever the subroutine specifies. At the end of the subroutine, we'll go back and check that one thing that we remembered a little bit earlier so that we know where to go to continue execution. That's what we need to do. Okay? As it turns out, in assembly, you can use fairly simple instructions to do all of these. To call a subroutine, it is exactly just call f. The instruction is call. It's not cal, C-A-L. I have no idea why move is MOV, but call is just C-A-L-L. There's some sort of inconsistency here. And to return is RET, just return. All right, so this is kind of cool. And we'll just go ahead and implement the end of the C function here, the main function. So we'll move 1 into EAX, move 0 into EVX, and ask the operating system to get me out of here. Yep.
This is a cisp instruction, right?
This is a
cisp?
yes.
So this
Yeah,
doesn't
call and
exist.
return are cisp instructions, but many RISC architectures also implement these two instructions simply because they are used so often.
It seems like you could do the same thing with like a memory label.
Yes, you can.
Like you
So
could
we'll
save. Yeah.
Yep, absolutely. We'll get to that part. But we'll talk about call and return first because they are very easy to understand and they're very concise as well. So we'll use call and return first, and then we'll think about how can we do the same thing without using call and return. Okay. So the next thing is we'll go ahead and assemble silly.s. No drinking in the classroom. Sorry. I have good hearing. Even if it's not fizzling, I can hear the gulp. All right, so GDB silly, and we have our program here. So what we'll do is we'll put a breakpoint on. Oh, I forgot to put a no op in front of the call instruction. I cannot really put a breakpoint on call itself. And I think it is pretty important to do that. So I'll go ahead and change the program first. Give me a no op instruction so that I can stop with the call instruction. And we'll put a breakpoint on line 20. Run the program. We are just about to call the subroutine. So the question is, what do you think the call instruction is going to do? Well, it actually does. It will do 3 things. Okay, instead of 2. Remember the push instruction will do 2 things. This will do 3 things. Yep.
So a question: how does the return know what to return?
Well, the function doesn't say return anything, so there's nothing to return. There's no value to return. It is simply returning back to main so I can finish up the rest of the program.
Will you talk about emulating returning in C? Because like one of the things you do in C is.
Oh, we will get to that point, but not right now. Yeah, because that's actually it's actually very simple, but at the same time it's kind of complicated in a way because I don't want to talk about returning a value until I talk about parameters and stuff like that. Yep.
Is it going to return to the next line of the call?
It will return. Well, we'll find out. Okay, we'll find out exactly what it's going to do. All right. So this is the call instruction. What I'll do is I'll look at ESP first because I kind of suspect it has something to do with the stack. So I'm going to take a look at the stack pointer before the call instruction, and then I'll single step, and now we are inside the subroutine. Line 10 is right here, and it is inside the subroutine F. Are we doing okay so far? So there is some kind of there's a jump involved when you use the call instruction because we're continuing execution at the label F. Is that part okay? But behind the scene, there's more stuff going on. So we'll take a look at the stack pointer as well. You can see the stack pointer is now 4 less than before. Just like with the push instruction. The question is, what exactly is it pushing on the stack? That's the next question. Well, we know how to take a look at that. We say x/wx $ESP so that we can look at the 32-bit thing that ESP is pointing to, which is the last item that we push on the stack. It turns out to be some kind of weird number. But that number isn't all that weird. If you look at this number and look at this number, don't you think they're pretty darn close? They're only off by 5 bytes. This one is D, so you have E, F, and then 0, 1, 2. They're off by 5 bytes. Okay? So we'll keep an eye on this location, okay, because this seems to be a pretty interesting location. We should keep an eye on it. Right now, our execution point is on line 10, which is inside the subroutine. We'll go ahead and execute the instruction without even checking anything because we are not really interested in what the subroutine does, but we are interested in how the return instruction works. We already know everything, like the ESP at this point. We also know the content on the stack at this point. So we'll go ahead and just single step through the return instruction. And we are now continuing on line 22. All right. So it's time to take a look at ESP one more time. And it's back to what it was. In other words, the return instruction has some kind of implicit pop in it because it does something that is similar to pop. It changes the stack pointer. The question is, what is it popping this address into? Well, let's take a look at all the registers and see if we can find it. Can you find it? EIP. So what do you think EIP stands for? The E is just extended, so it's not really an important part of the name. IP stands for instruction pointer. In other words, EIP is a register that tells you what is the location of the next instruction that the computer, the processor, is going to execute. Okay? That's what the return instruction is doing. It's doing a pop, but it's popping whatever the stack pointer points to into EIP so that you continue execution at where that location is indicating, or where you continue execution based on what you remembered, what you stored on the stack a little bit earlier. So here's the unfair advantage to people who took cisp310 from me. Can you relate what you learned in P300 when we talk about subroutines to what you are seeing here? Kind of? Okay. There's another way to do it. People who took P300 from me will go, wow, man, this is so boring, because I'm going to use a spreadsheet to trace a program. For those of you who have not taken cisp310 from me, this will be new. Okay, I don't think anyone have really done this much. Okay, so what we'll do is we'll say here's my call instruction, call F, and then we have the subroutine. Okay, here's the subroutine F. Has an instruction in it. Add L $1 EX here, and it has a return instruction. And here's my main. I'll just call it underscore start. And we are calling F, so we have to call F. And here's my own instructions. Okay, so I'm using a spreadsheet to type a program. Doesn't seem to be very, smart. All right, so here's the program. I'm going to use another window to take a look at what exactly is going on when I execute this program. Now on this side, what we'll do is we'll do instruction location. So this column doesn't serve any purpose other than indicating, okay, exactly which instruction are we talking about? Where in the program am I executing? Okay. We'll have another one here, which is our stack pointer. Okay, so we have, well, no, not the stack pointer. This is actually the content of the stack itself. Okay. And then we have X. Okay, we should indicate X first, so we'll put X here. X is a global variable, and in this case it has an initial value of 0, and that's my precondition. If you haven't taken P300 from me, just kind of bear with me at this point. the stack has nothing in it at this point. Okay, I can say that the stack is empty. It's not really empty, it's just that we don't have anything that we have stored on the stack at this point. So from my perspective, it is empty. There's nothing on the stack that belongs to me. So I shouldn't really be modifying anything. All right, we start execution at start. Okay, so we'll just say this is underscore start. Nothing is happening to X, so I'm not gonna write anything down here. But what we're gonna do is we'll put something on the stack. What do you think we're putting on the stack? How about, go ahead.
The address of start.
The address of the return point. Okay, once I'm done with the subroutine call, where am I supposed to end up at?
What do you call the sub-address?
The call is at quote unquote address 6 over here. So when we come back, we should continue at 7. Okay, we can only use line numbers here because I don't know exactly the length of the instructions. So the stack is going to store 7 because we are supposed to continue execution at location 7. Are we doing okay so far? This column is locations. These are the actual code or instructions. So now where do we continue execution? Yep.
So by just creating the start variable, you create, you add to stack by just creating the variable right there?
No, the stack is always there. It's just that now I put something in there.
We're just creating that label,
Creating what label?
the start.
No, the start label is just indicating where I'm executing. In this case, I can just say line 6. I'm executing on line 6. Yep.
I'm confused why we're talking about the start label when the call happens at call F.
Because the start label marks the point of the next item. Start is saying call.
Start is also what you put at the beginning of your program.
It's the entry point of the entire program.
So why does the start create the return?
Start
rather than
does
the call
not
to
return.
action?
It does not, but the execution of the instruction at that location did. Start has nothing to do. I mean, the label start does not really do anything. All it does is all that it is a label. It's a bookmark saying that, okay, this location is also known as start.
Okay. So I was understanding it up till this point that the call instruction is what put that address on the stack. Is that
Correct. Yes, that is correct.
Okay.
But it also does one more thing, because the next thing it does is we will continue execution on line 2. Okay? So in this environment, we are only talking about line number because that's the easiest thing I can do is to use line numbers instead of actual memory locations. Okay? Line 2, is going to add 1 to X. X goes from 0 to 1, no big deal. Then we go to line 3. Line 3 is going to do one thing. It's going to do 2 things. It will look up on the stack and say, okay, whatever I just pushed on the stack, I'm going to use it to let me know where to go back to continue execution. Well, it's going to look at the stack. It has 7 on it, so it will say, okay, we'll go ahead and continue execution at location 7, or line 7 in this environment. And then it will do one more thing. It's going to clear the stack of that thing. So in other words, we'll use a strike out symbol to indicate that this is no longer on the stack. Or, the stack is empty again at this point.
So we have line 2 there.
Mm-hmm. You mean row 2 or line 2? This is row 2.
4, where
row
you have
4.
2 in the instruction location.
Okay.
Does the stack then have 3 in it?
The stack has 7. 7 is still there.
It's still in there.
Yep. Yep.
If you do additional pushes and pops in your subroutine,
Then you will have more stuff on the stack.
how does the IP pointer know which part of the stack to pop?
Whatever ESP points to.
Whatever ESP points to.
Whatever ESP points to, when you execute the return instruction, it will just take the 4 bytes pointed to by ESP and use those 4 bytes to indicate where to continue execution. So if you mess up on the stack and those 4 bytes points to La La Land, then you will try to continue execution at La La Land, which is good because La La Land probably is a location where you're not supposed to execute and you get a segmentation fault. The worst thing that can happen is it is not exactly La La Land. If it is not exactly La La Land and it's actually inside your program, then you will return to the wrong point of your program. And then really, really bad things will happen. Because your program doesn't crash right away, it will just crash later. But by the time it does crash, you cannot explain why it crashes. So it's always good to just go to La La Land, just die right away instead of getting poisoned, and live a little bit longer. Okay, so we continue execution at line 7. Line 7 is basically the end of the program, so I don't really need to trace the program anymore. So in this particular representation, each column on the stack really represents, like a 4-byte chunk in reality. In this case, 7, which is just a line number, really should be replaced by the location of the instruction next to the call instruction. Okay, I just want you guys to start to get used to this representation, because later on we'll be stacking more stuff. Okay, we'll be putting more stuff on the stack, and this particular notation will become handy. This is the first semester I try to use this approach to explain things in the assembly programming class. So at first I think there may be some confusion. Columns represent memory locations. Rows represent a particular slice of time. It's a snapshot in time. When you have a value here and this is an empty space, it means it is not changed. When you see a bar, that means the stack pointer is moved back to that side from your perspective. It is the stack pointer, instead of pointing to column C, is now pointing back to a location where you're not supposed to touch. Okay. Are we doing okay so far with this notation? Okay. Because I think this is a good notation, especially later on when we have many different items on the stack. This really will help to illustrate when do we get what item on the stack and how do they relate to each other in terms of location in the stack. So we'll continue to use this particular method. All right, so now that we are back to line 22, I can just continue the execution of the program and be done with it. Okay. Are there any questions at this point? No questions? Okay. Yep.
Actually, never mind. I just answered my own question. Okay.
Very good. Those are the best questions. All right. Now let's go back to this program and say, could we have changed the call instruction and use instructions that we already know, the really, really basic instructions, and could we have changed the return to use also the very, very basic instructions that we have learned already? The answer is obviously yes. So we'll go ahead and copy this program so that we keep the one that is pretty simple and replace it with something that uses all the basic instructions that we already know. Okay. All right. So the call instruction can be replaced by a push and a jump. Okay. So we already know the push can be broken up into a move and an add. I should say an add and a move. So I'm going to just use a push out here and followed by a jump instruction. The question is, what exactly am I pushing on the stack? I have to push the address of the next instruction, right? So the easiest way to do it is simply to say that this is L0, and I'm pushing $L0 on the stack. I'm saving the return address on the stack. Then I'll go ahead and continue execution in subroutine F, or go continue execution at label F. Is that okay? Yep.
You're basically doing the same thing?
Yep, it's the same thing as a call. Okay. And then how about this return instruction? Well, let's try something like this first, because it is kind of like a pop instruction, except it is popping into EIP, the instruction pointer. So we'll see whether this works or not. I really don't know whether it will work or not. So I'm just wrong program. Silly 2. Okay, we don't have direct access to EIP. In other words, we don't have access to the instruction pointer itself. Do we have anything that can indirectly change EIP? Go ahead.
When I was thinking about this, it seems like you could have a dedicated return label, and then you could just modify that label.
You cannot have a dedicated return label, because if you have a dedicated return label, then every single time f returns, it's going to return to that point. You cannot call f from multiple places.
Well, what if instead of having a push instruction, you had a move instruction, and then you changed the content at that label to match the address where you want to go back to?
But we are using the stack for the same purpose.
I'm just saying, like.
Well, there are, okay, in a long time ago, when programming languages first tried to implement call and return, that's exactly what they did. Each subroutine has a particular spot in memory to remember the return point. There's one problem with this approach. It cannot do recursion. Because in recursion, what do you have? You have a subroutine calling itself potentially many, many times. So if a subroutine only has one fixed memory location to remember where it is supposed to go back, it will be overwritten several times, and you can only return from the last invocation, but after that you'll be lost. Okay, so using the stack solves that problem, because now you can have multiple return addresses on the stack. All right, so this doesn't work. How about something like this? I will return to EAX, and then I'll use a jump instruction and say, oh, don't jump to a particular label, jump to the location according to EAX. We haven't seen this particular addressing mode before, but what it does is simply to say, instead of jumping to a label, look at the value of EAX, we'll go ahead and jump to that location. It is not the same as the parentheses, it's not indirect addressing here. If you put indirect addressing here, then it will use whatever EAX points to become the address that you're going to. This way, it is just using EAX. It will branch to the location pointed to by EAX. If you put parentheses around it, then it will first do an indirect access to a location, and then use the content at that location to tell where jump is supposed to jump to. Okay.
So this way is just more efficient?
This is the only way to do it.
Okay.
Okay. The effect of this is to say EIP is the same as EAX. That's basically what it's doing. Okay, because I don't have direct access to EIP. So this is the other way to do it, because all it does, it really is the same as move L %EAX, %EIP. But since I don't have, that instruction won't work, this is effectively doing exactly the same thing. Okay. But the most important part is I have a pop instruction. Whatever is on the stack right now is what I will retrieve, and I will use that to indicate where I'm supposed to go to continue execution. Yep.
Does it do anything at all, the jump instruction, if you just don't have an asterisk there?
It will not take it if you don't have an asterisk.
Okay.
We can actually give it a try. I believe that will give you an error message. Indirect jump without asterisk.
Okay.
So that's exactly why you have to put an asterisk there, because
At least it tells you exactly what to do.
yeah, very rarely it will do that. Yep. Okay. So now that we have this program fixed up, not to use call and return, we still want to double check it will accomplish the same thing as a call and a return. So we'll go ahead and assemble and link the program. And go ahead and make sure that we trace this program and make sure that it still does what it is supposed to. So we'll put a breakpoint on line 21. Run the program. We push L L0 on the stack, and then we'll continue execution inside the subroutine. Now we're in the subroutine because you can see from the line number we are now on line 10. We'll do the only thing we are supposed to do in the subroutine, and now this is the return code. It's going to pop whatever we push on the stack into EAX, and then it will continue to jump or continue execution at where EAX indicates. And where is that? It is exactly on line 25. And line 25 is the correct place. because line 25 is the move out instruction, which is the instruction right after the jump instruction. So it did accomplish, exactly what call and return, would do, except we did not use, the call and the return instructions. So are there any questions about, call and return? Now in this class, from this point onward, we'll just go ahead and use call and return instead of this method because, we are doing, assembly language programming by hand. So, I think it is not worth the time or the effort to really break it up into these smaller instructions. Yep.
Was it in the subroutine where EAX got the address at L0? When did EAX get the
pop out instruction?
Right there. Okay. And that was in the subroutine?
That is inside the subroutine. So let's take a look at it again, and if there are any questions, we'll try to address all those questions now. So the most important parts would be this part here. This is the return code, and also here, this is the call code. Any questions? Any questions? Right. If there are no questions, we'll go back to the notes, and I think we're pretty close to being done with subroutines already. There's really not much to say about subroutine. Okay, calling and returning. And it's the same thing. The first slide talks about subroutines. The next slide talks about, calling. And then you have, a return code here, just like what we have talked about already in the class. The call instruction passes control to a destination specified by the only operand. This operand must be of memory mode. It can be direct, indirect, and so on. The return instruction returns to the instruction immediately following the most recent unreturned call. Now that is not exactly right, because the return instruction really just use whatever is on the stack that your stack pointer is pointing, and use that as the return address. It is not necessarily a good spot to land. Okay, let's see what we mean by that. Okay, so we'll go ahead and trash our program. We'll take silly.s, go to badsilly.s. Okay, because this one is going to mess up the program. Okay, the way it's going to mess up the program is, oh, okay, I think I need to remember something in EAX, but then I forget to pop it. Okay. So we'll go ahead and assemble G-stabs. All right. So here we have bad silly. Instead of just going line by line, we'll just go ahead and run it. Okay, keep our fingers crossed that it will crash, and it does. In fact, it crashes in a very strange way because it says the program received signal seg fault. Basically, what happens is the processor is configured to know where this program is allowed to execute from. If your program tries to execute from locations where it's not supposed to, the processor will actually get an quote-unquote interrupt to say that, okay, something bad has happened. And this turns out to be called a segmentation fault. But what is even more interesting is this, the whole bunch of zeros here. Because what it is saying is the segmentation fault is generated when your program was trying to execute from location 0. Why does it want to execute from location 0?
That's what's in EAX.
That's exactly right. Okay, that's whatever is in EAX. So now that we suspected that's the problem, we'll go ahead and put a breakpoint on line 12, which is where the return instruction is located. So right before it returns, we want to stop and say, okay, does the stack make sense at this point? Run the program again from the beginning, but this time it stops before it crashes. So at this point, we will take a look at ESP. It is this number. And we'll go ahead and take a look at two 32-bit things on the stack where the stack pointer is pointing at. Okay, these are the 8 bytes on the stack right now. this is what the return instruction will use to return when it should have been using this one. Okay? And that is why the return instruction is going to location 0, generating the protection fault or the segmentation fault. Are we doing okay so far with this? Yep.
So is it just using the last thing that was put on the stack? Is that how?
It's just using whatever the stack pointer points to as a return address when you use the return instruction. Okay? Are we doing okay so far? Okay. We'll go ahead and make this program even worse. Yeah, that's the whole purpose of this class, is to show you guys, how bad can get worse and so on. Okay, so. And this time, instead of pushing something on the stack, which just causes it to crash, we'll do something kind of even worse. Okay, we'll say, well, let's go ahead and do something to the stack point, whatever the stack pointer points to. Okay. In fact, let's go ahead and make this even a negative number. Okay, -5, whatever, 6. Okay. Okay. So what this instruction is doing now is it is going to subtract 6 from whatever the stack pointer is pointing to. The stack pointer is now pointing to the return address. So my return address is now a little bit off from what it is supposed to be. Okay, so we'll go ahead and track down this program and see what it is going to do. I really need to teach you guys how to use the makefile so that I can use it. Alright, so here's the program. And we know the program is going to be fine until we get to the return instruction. So we'll put a breakpoint on line 11 because everything should be okay before that point. So we'll run the program, and now we are ready to return. According to this program, when it does return, it has to return to the instruction after the call instruction, right? The call instruction is on line 20, and if you list from line 20, the next line is on line 22. So when we return, it should be going to line 22. A single step, and it said stop due to shared library event, because it landed on the spot where it is not even a valid instruction. Okay? And why it is saying it is a shared library event, it's beyond my understanding. But it did something that is not crashing, and it's not correct behavior. Now, if you craft that number correctly, you can actually make it land on the no-op instruction. Okay. I think we can actually show the addresses of the no-op instruction by using the X command. Because when you say help X, one of the options is to show the instructions. So let's try it. Let's go ahead and try this. X/, okay, I think I only need 2. Let's make it 3. So X/3I starting at location start. Okay, so this is really cool because what it does is it shows me the no-op instruction is at location 7.9, and the call instruction is at location 7A, and the move instruction is at location 7F. What is the difference between F and 9? A, B, C, D, E, F, 7. Okay. Doesn't sound right to me. 6. Okay. It doesn't sound right because 9 and F are both odd numbers, so the difference should be an even number. So it actually is 6. Okay. So that means it really should be going to the no-op instruction. If you subtract 5, then it will go back to the call instruction. Let's do that instead. So instead of subtracting 6, we'll go ahead and subtract 5. And then we'll put a breakpoint on that return instruction. So B11. And we'll run the program. single step. We're back to the call instruction.
Alright, I like that.
Yeah, continue execution, single step to return instruction. We're back to the call instruction. What if I delete that breakpoint and continue execution?
Just keep going.
It becomes an infinite quote-unquote loop. It's not exactly a loop in the sense of jumping to a location, but it is a loop in the sense that it will never break out of it. Okay? Does everybody understand why this is now infinite? Because I just crafted the program, or crafted the corruption of the stack so that the return address is 5 less than what it is supposed to be. And so instead of landing on the instruction following the call instruction, it is actually back to the call instruction itself, making the program to call again, but every time it returns back to the call instruction, and therefore it never stops at this point. Okay? So I'm going to use Control-C to stop the program, which is really handy, because now it is back to here, and now you can also look at what is on the stack, because now at this point, you can look at x/wx $ESP, find out what it is supposed to be, single step, and then look at it again, and you can see, oh, this is bad, because the return address just got changed. Okay? So let's get out of this, and then go back to the source code. And then some people will have the question and go, but who in their sane mind is going to do something that silly? You know, trashing the stack intentionally and stuff like that. Nobody, I can tell you, nobody is going to do this unless they're trying to demonstrate the concept of what you can do to the stack to mess up execution. But what if I tell you that your local variables are on the stack as well? If you have a local array, it is on the stack as well. Okay? Now that part is a little bit later, we'll talk about that later. But this can happen, not exactly in this context, but the effect of something like this can happen if you did something like this in C. Okay? If you do this in C, like some array bracket, XYZ minus equals 5. It all depends on what XYZ is, because this array, if you index this array out of range, then it will be going to somebody else's portion of the stack. What if that portion of the stack so happens to be the stack pointer? I mean, not the stack pointer, but the return address. Then you end up with exactly the same effect as this. You can in fact do this in C. You can craft a program to do this intentionally in C. Yep.
I'm kind of wondering, you said that the local variables are put on the stack, so
yep.
If you're writing a C program and say you dynamically allocate one array and then a second array, and then you do delete on the first one, because it would be the second to last thing on the stack, would it have to?
Okay, let's backtrack a little bit. New and delete do not apply to the stack, because that's in the heap. But your local variables, are on the stack. Okay. Okay. Since we are already here, we might as well do this in C. Okay. So we'll go ahead and try to emulate this program in C. Okay. Well, we're having a lot of fun here. So we have subroutine F. And let's say it has int array bracket 1 has one single element. It is an array. And then we will go ahead and say, okay, now I have to do some counting. Okay, so here's this. We haven't really talked about that part yet, so I have to do all the counting in my head because we haven't really talked about it. So the local variable, okay, I can show you, but we'll talk about this later. The local variable is always at the lowest portion of the stack. And the stack pointer typically will be pointing to your local variable at that point. The next item up is the save EBP. We'll talk about that too, so don't worry. I'm just doing some counting so that I can craft the program to crash exactly the same way. And then we have the return address here. So, and this is 32-bit integer, so that means array bracket 0 is here, array bracket 1 is here, array bracket 2 should be our return address. Okay? And in order to call this subroutine from main, the last instruction that executes should be a call instruction, because that's exactly how a C program is compiled into assembly language. Okay? So that means if I say array bracket 2 minus equal 5, it should accomplish the same thing as the assembly version of this program. I'm trashing something on the stack, and it so happens to be the return address. Okay. So exit, and then we'll go ahead and run this program, but in GCC, in GDB. So I'm going to use -G to include a debug symbol in the executable. Where's silly in C? Where's silly.c? Oh, forgot the -O. Okay, there we go. GDB, where's silly in C? All right. We put a breakpoint on line 5. Run the program. Now we are on line 5. The first thing I'm going to do is to take a look at, okay, what exactly is look at array bracket 2? Print array bracket 2, and some really weird big number, /x, not so weird anymore. Okay. In fact, we'll do even better. We'll say what exactly is at that location using the x command. X/A means disassemble disassemble the content at a certain location, and we'll just say $2 because when you see a $1 and a $2, that means you can refer to those values using the dollar symbol. It helps to simplify things a little bit. Okay, it says it's main plus 8, and it's a B8. It really should be a return address. Maybe it's actually at a higher location. No, that's a frame pointer. No. I'm hunting for that value. Maybe it's just 1. No, that has to be it. Well, let's see whether it works. Single step, and now we're back to the call. And then it goes again, it goes again, it goes again, it goes again. This program, if I continue execution, let's stop the breakpoint, delete breakpoint 1, continue the execution of the program, has exactly the same effect as your assembly language program. But when you look at the code itself, does it look that suspicious? Now, it looks suspicious only because the reference to array bracket 2 is right under the declaration of array 1. What if the declaration of array 1 is defining some really big number, and the dereference, not dereference, but the indexing, the use of the array element is using a variable, and the variable just turns out to have the wrong value? Then it's not so obvious anymore. And it can still accomplish the same thing. Someone who only understands how to program in C and C++ will be kind of scratching his or her head when this program does not exit. Okay? Because this program doesn't even crash. If it did crash, it would have been better. But it did not crash. It did not even do anything suspicious. It's just that when F returns, it returns to the call itself. Okay, so are you guys starting to see, how important the stack is, and also why C is a bad programming language?
Should have told me that last semester.
Well, I can explain why C is a bad programming language. Because C was never intended as a beginning programmer's language. It was never intended as such, and that's why it leaves all kinds of ropes long enough to shoot yourself in the foot. It has guns, it has chainsaws,
Landmines, grenades.
Oh yeah, it has tons of landmines, and that's why. Okay, C really should not have been used as a introductory programming language. It really should not have been. But at some point, the universities, changed their standard. Instead of using Pascal, which is a much better protected language, they switched from Pascal to C, and we just have problems like this. Okay. And I think that's really the value of this class. I mean, the value of this class is not to train you to become assembly language programmers, but rather so that you understand your C and C++ programs well enough that when you see something that is really suspicious, you kind of think about the low-level implementation of your program. Then you can start to understand, okay, so if I did something like this, it can cause problems like what we just saw. Okay. And I really think that really is the value of this class. Not that you will write assembly language programs that are 3 million lines long, but rather when you encounter problems that you cannot explain in C, you can drop down from the C level to the assembly level, and you can start to look into, okay, am I corrupting some sort of memory that in the end will cause a problem, a symptom that I'm observing. Okay. Right. Any other questions about call and return? Two little very innocent looking, instructions. They're just using the stack. But because you can do all sorts of stuff to the stack, you have to watch out. All right. If there are no questions, I think we're done.
I have a question.
Go ahead.
So, is there something that we can use besides the stack, like a scratch area of memory, besides using labels, that we can use like it? I
For
see
calling and returning?
No. Like for your, I know we could use the stack for our own purpose besides returning and calling, but is there any other that we can use?
No other easy way.
So.
When you're programming in assembly, you have some control. You can actually say that, okay, I don't want to use call and return and the stack pointer, and you can dedicate one of the other registers as quote-unquote your stack pointer. So it would use an entirely different area, just for the purposes of call and return. You can do it when you're doing it in assembly, but when you're writing a program in C, you don't get a choice. The C compiler decides to put everything on a stack, and you don't get a choice. So everything is on a stack, and when you try to access an array element out of range, then bad things can happen, just like what we observed. So there's no way around potential dangers of doing this sort of thing. It's mostly also because in C there's no way to check the boundaries of the index when you do indexing operation, because inside the C compiler, array is really treated like a pointer. The size of the array is not carried with the variable itself. So that's why you always have this danger of accessing an element out of range and trashing something that is important on the stack. All right. Any other questions? Go ahead.
Sorry, why don't they fix that in C? Why don't they create another stack?
Because C was never intended to be a protected language.
No, I understand, but wouldn't that be an easier fix? They just to create another location memory, like if you declare anything without using functions, would use specific memory, and then you will have a second stack just with
but something like this will still be trashing something else. It's just not a return location anymore. It's something else. So you can fix certain things, but you cannot fix everything. And the root of the problem is in the C programming language, it just doesn't do bound checking on the index before it performs the operation. It's really something that you cannot fix. It's part of the language. How many people remember why we have the C programming language? How it came into existence?
After the B programming language? It came in after the B programming language?
It's after the B programming language, yes. Okay, one of the original creators of the C programming language passed away, and I think that's about 2 or 3 weeks after Steve Jobs died, and nobody cared because nobody cared. He's just an old man, looking kind of old, and and nobody cared. Okay, because everybody is saying, "Oh, how Steve Jobs is so wonderful." If it's not for him, computers would not have been, taken to this level, and so on and so forth. Well, without the other guy, what was his name? Richie. Okay, Richie. Okay. See, I just made my point. Okay, so without Richie, then there would have been no Unix. If there were no Unix, there would not have been Mac OS X, because Mac OS X is built on top of BSD. BSD, which stands for Berkeley Standard Distribution, is a version of Unix. And Unix was originally conceived in the Bell Labs, and this Richie guy was one of the original 2 authors who not only wrote the Unix operating system, but as they were writing the operating system in assembly language, they realized we could never get this project done in time because we're all crafting little instructions, and C was invented as a shorthand so that they can do assembly language programs much more efficiently. It was never supposed to be released to the wild. Okay. So that is why we have things like these. From the get-go, C was all about allowing low-level access as much as possible. Your pointer stuff and your array indexing stuff are prime examples of low-level access. And also efficiency. Bound checking means a loss of efficiency. And that's why it was never done. Okay? So there you go. You have a little bit of the history of programming languages today, on top of call and return.
Now my life is complete.
Yes. Okay, so this is actually my new notes on the same topics, so you should probably read that too. It's really the same thing, except it is written in a different way, slightly different way. So same thing, since we covered that already, we'll just kind of move on. And here's my own homework assignment, which is always fun, to watch Tak do his own homework assignment. Implement print hexadecimal, but recursively and without using any dot data constructs. Use EAX as the number to print in hexadecimal. Okay, how do you print a number in hexadecimal?
You convert it from decimal and print it?
Well, to print it in hexadecimal there are several ways to do it. Okay, let's take a look at how do we print a number in hexadecimal, which actually is easier than your homework assignment. Your homework assignment is generalized to deal with any basis, but printing in base 16 is particularly easy. Okay, so you look at a number. I'm going to use mousepad so I don't use the whiteboard. I don't think I will do it today, but I'll do it next Tuesday. Okay, so when you look at a number, a 32-bit number, let's say, okay, a 32-bit number, okay, let's make it easier. Let's look at an 8-bit number. An 8-bit number has exactly 8 bits. So the question is, how do I print this number correctly? We don't have a shift operation, but we can use a divide, to get the least significant 4 bits out. But then you'll be printing the least significant 4 bits first before you print the most significant 4 bits. Right? And I don't want to have any leading zeros either. Because your program is going to print a whole bunch of leading zeros, which is not always appropriate. So the question is, how do I do this without printing leading zeros? Well, first of all, how do you do this in C? How do you print a number in hexadecimal without leading zeros in C? Let's switch back to a command prompt like this one, and we'll just go ahead and look at this print hex.c, and we have to pound include.
IOStream is a bunch of tags you could probably use. Using the cout, you could
I'm not doing anything high level. Okay, I'm using C, very basic C stuff. I'm not even using printf or putchar. I'm using write, like system surface number 4 that you guys have to use. Okay. So here's my print hex subroutine, and it's going to take no parameter because I haven't talked about how to use parameters yet. So the number that I'm going to print, I will basically put it into a global variable n. Now, how do I print a hexadecimal in this case? I need something that's local to this print hex here. So I'm going to use a char ch, which is something I can push on the stack. Okay. And then what I'll do is I'll take a look at n. I would say if n equals to 0, then I'll just go ahead and print it. Okay. And I'll also indicate what ch is supposed to be. Ch is going to be n mod 16 plus, and then if n is, okay, I'm not sure whether I should do it the quick way or the slow way. We'll do it the quick way. I mean the slow way. If ch is less than 10, then ch plus equal 0, else ch plus equal a minus 10. There we go. Okay. And then we'll determine when we can do the recursion and when we cannot do the recursion. Okay. Then we have to say if n, we have to change n too. So n is going to be n divided by 16. If n equals to 0, then there's no need to do recursion. So that means if n is greater than 0, we have to do recursion here. Print hex. Okay, I don't see any write here. In other words, even though I have ch ready to be printed, where should I print it? Okay, let's go back and look at how I prepare ch. Ch is n mod 16. In other words, I'm taking the least significant 4 bits of the number and extract only that part out and put it into the variable ch. Okay? What do you think is the range of the value of ch? It can go from 0 to 15, okay? Which is the range of a hexadecimal number. But in order to print a hexadecimal number, I cannot just print out the code 0 to 16 because those are unprintable characters. The ASCII code, the character corresponding to ASCII 0 to ASCII 15 are non-printable. So in order to make it printable, I will have to say if ch is less than 10, we'll go ahead and add the ASCII code of 0 to that. In other words, I'll be adding the ASCII code of 0 as long as ch is from 0 to 9. Okay, what happens when you add 0 to the ASCII code of 0? What do you get? You get the ASCII code of 0. Is that printable? Yep. What do you see when you print the ASCII code of 0? The digit 0. Okay, very good. So that means this will handle all the cases from 0 to 9. What about the values from 10 to 15? If ch is not less than 10, it must be from 10 to 15. In that case, I'm going to do the following. Because what I'm doing here is I'm taking the ASCII code of lowercase a, and I'm intentionally subtracting 10 from it. Because ch starts with a value of 10. If ch is 10, then what will be the value of ch after this calculation? It will be the ASCII code of a. And that's exactly what is representing 10 in hexadecimal. The letter A is representing 10 in hexadecimal. So I do have ch ready to be printed after this line here. The question is, when am I supposed to print it?
After the recursion.
After the recursion, exactly, because I have to print the more significant digits first. So here is the only time I should say, this part here. Okay? Well, let's check whether it works or not. That will be the last thing we do today. And then on next Tuesday, I will turn this into an assembly language program. We haven't really talked about local variables, but since we know how to use the stack, we can accomplish the same thing. So in this program, we just print hex. Okay, no, feed dad is 1, I'm hungry. And we also print something else, that does not have leading zeros. So just to make sure that this program stops in time, it doesn't print leading zeros. What should I print here? Just bad. Bad dad. Yeah, just bad. All right, so we'll go ahead and return 0 and see whether this program works. GCC-O print x.c. Too many arguments. Oh, okay. Because I'm not supposed to use. Parameters, so I'm using n as my parameter. So I have to do it like this. Feed that and equals that. Yeah. All right, so let's give it a try. Hey. And it prints just bad here. Where's the first number? Oh, okay, I know why. This should have been. I got bit by my own, These should all be unsigned, because what is this number? What is the sign of this number? Feed dab. It has F as the most significant 4 bits. F is 1111, so that means the most significant bit of this 32-bit number is a 1, which means the number is negative. And if this number is negative, it's not going to work because when it gets to this part here, it's not going to do the recursion because n is negative already. So it will skip this thing and it will just print the ch. But ch is going to be wrong because a negative number mod 16 is just going to be probably another negative number. And so, it's printing a symbol instead of a letter because it is on the other side of the ASCII code of 0. All right. Okay, now we can try it again and run it. And it worked. I forgot to put the line feed. So we have the first one here and then the second one here. Okay. So it's all done by recursion, and so next time we'll talk about how do we do that inside an assembly language program, even though we haven't talked about local variables. Yep, question? No? Okay. All right, so don't forget your homework assignment, and which is due next Tuesday. Have a nice weekend.